Hello, hello. We're here on resonance in crystal glass and how we get that to break. On our first slide, you can see our photo of a wave. It has a crest, a trough, the amplitude, and the wavelength. These are the typical visuals you'll see on a sound or light wave. And as such, let's go further into the definitions. We have the crest, which is the maximum distance from the equilibrium in the positive direction, as well as a trough, which is the maximum distance from the equilibrium in the negative direction. They both have magnitudes, which are positive. It's just the direction that changes. We have a wavelength, which is the distance in meters between the two crests or two troughs. Followed up is the amplitude, which is the displacement from the equilibrium point, also known as the magnitude, or it's measured as the magnitude from the equilibrium to a crest or trough. Now, what weren't labeled on that graph was the period and frequency. The period is the time it takes to make a full rotation or oscillation in the cycle. Frequency is the number of periods given in a set time or within a second, typically. To go over their signs, the wavelength is typically represented by lambda, which is measured in meters. We have the wave speed, which is velocity, which is meters per second. Amplitude, which is represented by A and is also represented in meters as the magnitude described beforehand. We have the period, which is a capital T and is used in seconds. The capital T should not be mixed up with the lowercase t, which typically represents time. Frequency is given by a lowercase f and is measured in hertz. We also have angular frequency, which is measured through omega, which is a radians per second. This is different from frequency as it's a rotational base. We have our equations here. For wavelength, we have lambda equals the velocity times the period. We also have the wave speed, which we'll be using in our demonstration today, which is velocity equals lambda times the frequency. We also have this equation for amplitude, which is a displacement of sorts, which equals the amplitude number by sine omega time. And then we have this other symbol in here, which is the phase shift, which is the displacement from the y in the graph. We also have period, which is 1 over frequency. As you can see, these are also interchangeable with the frequency equations I have here, which is 1 over period. Another frequency equation we have here is wave speed over wavelength, so velocity over lambda. Our last one is our angular velocity, which is omega equals 2 pi over the period, or 2 pi frequency.
Why does crystal glass shatter at a specific frequency while others do not? The reason being that crystal glass will shatter at a specific frequency depends on the size, shape, and thickness of the walls of glass. The glass will begin to vibrate at within a range of frequencies. However, the frequency at which it will vibrate the most is going to be a peak frequency where opposite sides of the glass will vibrate back and forth opposite of each other, causing it to break. It is for this reason. It is because of resonance that it begins to. Now that we know that frequency is an important piece into shattering a crystal wine glass, what about volume? Does the volume of your voice or in other words, the amplitude of the waves that you create with your vocal cords, how much does that matter? Up to some point, it is important for the amplitude to be large enough in order for the transfer of energy into the crystal wine glass to be at its most efficient. However, just producing louder and louder and louder volumes does not affect whether the crystal wine glass will shatter. If it is not vibrating at the correct frequency, then the crystal wine glass will simply just shake. It will not be shaking, and it will not be shaking at the correct frequency in order for it to shatter.
I'm going to talk about environmental factors of a crystal glass to be broken with resonance. My first point is that the glass needs to be crystal, because crystal is pure and resonates all at one particular harmonic frequency, and the atoms line up in a crystal makes the wine glass vibrate just the right way. And the second point is that the glass must not be affected by damping. Wine glass is a good example because it reduces the amount of damping because it stands on a stem. And damping is just interference with a force which will act to prevent the glass from vibrating. So it will reduce the force which will prevent the glass from vibrating. And my third point is right frequency, the note. You have to match the resonant frequency of whatever glass you're trying to break. And the resonant frequency is the note at which the glass will vibrate. And wine glass, again, is a good example. It's very resonant due to the hollow tubular shape. And the fourth, you don't really need microscopic defects, but it will help tremendously because the little small cracks or defects within the glass, the the vibrations will open up that crack, and eventually the glass will break. And the fifth, yes, um, the resonance frequency of the glass, you can figure it out by flicking the wine glass or rim around the top of the wine glass with the wet finger, I guess. And it should be a clear tone. And the sixth, amplitude is very important because the tone from the flicking glass, the glass vibrates, and waves and air pressure emanate out of the glass, which our ears and brain interpret as sound. But amplitude is the volume of your voice or whatever object you're using. But that will help a lot. Driven oscillation is my sixth point. For the driven oscillation, the glass will try to move in its vibration further and faster than the material in the glass is able to move, and the glass will break under the strain. And yeah, I'm gonna go back to the frequency and the amplitude. You need to have the right frequency, the most important part. And you have to have high enough volume. So you have to match the pitch of glass, match your voice or whatever to the resonant frequency of the glass, and have at least 100 decibels
to break the glass.